Welcome learners. Today's chemistry lesson will be presented by Martin Bunguswa, and it is a continuation of what we had done previously on industrial processes. We had discussed the Haber, we had discussed the Austral, we had also discussed the contact process. Just a quick review of what we had discussed on the contact process. We have looked at what happens in the roaster, as you can see on the flowcharts on your screen, what happens in the purifier, what happens in the drying tower, what goes on the catalytic chamber, which are the conditions and why those particular conditions are suitable, then the heat exchanger, what happens in the heat exchanger. We went to the absorption tower. We were able to explain why SO3 is absorbed in common sulfuric acid and not in water. Then formation of oleum, then the dilution chamber, and how we get the sulfuric acid. Now, there is also a process called recycling that is required in the contact process. What is being recycled is unreacted SO3 and unreacted SO2. And the reason why they need to be recycled is in order, one, to minimize on pollution in case they get to the atmosphere. Because both gases, SO2 and SO3, when they get to the atmosphere, they combine with rainwater to form acid rain. And acid rain can kill vegetation, can also destroy limestone buildings. Another method of minimizing pollution in the contact process is through a process called scrubbing. In scrubbing, we pass the gases through a chimney that is lined with an alkali like calcium hydroxide, where neutralization takes place to produce calcium sulfite and water. Then the conditions required for the contact process to work, we have the vanadium 5 catalyst, 2 to 3 atmospheres of pressure, and temperature 450 to 500. Now we know that the forward reaction is accompanied by a decrease in the number of gaseous molecules. Therefore, it's supposed to be favored by high pressure. But ordinarily, we only use a pressure of 2 to 3 atmospheres. The reason why we cannot use too high pressure is because very high pressure requires highly pressurized equipment, which are very expensive to maintain. And that is why we only need to use a pressure of between 2 to 3 atmospheres. Again, the role of the forward reaction is accompanied by low temperature. But now if you use too low temperature, the reaction is going to be too slow. And that explains why a catalyst is employed in the process. Those on the screen are the equations for all the reactions that take place in the contact plant. Remember also the uses of sulfuric acid. Also the uses that we had discussed earlier on. We can use sulfuric acid produced here to manufacture soapless detergents. These are called sulfonated benzoate salts. We can use sulfuric acid to fill car batteries. We use sulfuric acid to manufacture some fertilizers like ammonium sulfate. So sulfuric acid can also be used in the laboratory as a drying agent for gases, and it can also be used as an oxidizing agent. That is the contact process. Our next process is called the Solvay. The Solvay process is used in the manufacture on large scale of sodium carbonate. In our country, Kenya, we get sodium carbonate from trona, which is mined at Lake Magadi. But in other countries where there is no trona, they can only get the sodium carbonate through the Solvay process. The Solvay process requires the following as the raw materials. One is brine. Where do we get brine? From seawater. We also need carbon dioxide, which you can get it from limestone. We also need coke. We also need ammonia, which you can get from Haber. That means the Haber plant can be located near the Solvay because of the availability of the main raw material. Then brine and ammonia are then reacted together to produce what we call ammoniacal brine. Ammoniacal brine is simply ammonia brine saturated with ammonia. We can precisely write the formula for ammoniacal brine as ammonium hydroxide plus sodium chloride. Then once ammoniacal brine is formed, the two are taken to the Solvay tower where they meet carbon 4 oxide, where the carbon 4 oxide is coming from the limestone kiln by decomposition of the calcium carbonate. Now the carbon 4 oxide, when it gets to the Solvay tower, it now combines with ammoniacal brine to produce sodium hydrogen carbonate and ammonium chloride. The equation for the reaction taking place in the Solvay tower, you can see it there on the screen. We have ammonia plus CO2 plus water to form ammonium hydrogen carbonate. Then ammonium hydrogen carbonate plus brine gives you ammonium chloride and sodium hydrogen carbonate. Now the two products, that's ammonium chloride and sodium hydrogen carbonate, then move on to the next chamber where filtration takes place. The reason why they are filtered is because they have differences in solubility. Ammonium chloride is much more soluble than sodium hydrogen carbonate. Therefore, on filtration, one of them crystallizes out very fast and it is removed. Remember, the process is not called fractional crystallization. It is simply crystallization process. Then, from there, the sodium hydrogen carbonate, which is obtained through filtration, is taken to the roaster. Now, inside the roaster, the sodium hydrogen carbonate is heated. And upon heating, it decomposes to produce sodium carbonate, which is our main product here, carbon 4 oxide and water. What is the effect of CO2 and water? The two products, carbon 4 oxide and water, are then recycled. They are recycled for the obvious reason to minimize on costs. Then sodium carbonate is removed. We have already gotten our sodium carbonate. Now remember, the Solvay plant is one of the most efficient industrial processes because most of the raw material, most of the products are reused in the plant. So we go back to the limestone kiln where the calcium carbonate had decomposed to produce calcium oxide and CO2. The calcium oxide moves down to another chamber where it meets water. The water reacts with the calcium oxide to produce calcium hydroxide, which is called select lime. The calcium hydroxide produced then reacts with ammonium chloride that had been produced from the filter. So the reaction between ammonium chloride and calcium hydroxide produces calcium chloride, ammonia, and water. Ammonia is recycled again. Water is also recycled. And the only waste byproduct which we get from the Solvay plant that is not used within this plant is calcium chloride. And that calcium chloride, however, can also be put to other uses. One of the uses of the calcium chloride is that it can be used as a drying agent. Calcium chloride can also be used during extraction of sodium metal. It is used to lower the melting point of the rock salt from 800 to 600. And that is how we get our sodium carbonate. On the screen is the flowchart that tries to summarize the essential processes that take place in the Solvay plant and also the equations for the reactions involved. Please note that there are three substances that are recycled in the Solvay. One is carbon 4 oxide, another one is water, and the other one is ammonia. And only one byproduct is eliminated from there. Now, what are the uses of the sodium carbonate obtained from this process? One of the uses of sodium carbonate is softening of hard water. And how it softens the hard water is that it supplies the carbonate ions, which may react with the calcium or magnesium ions, and they are precipitated. Another use of sodium carbonate is in the manufacture of glass. Not really that is used, but it is mixed with something else during the manufacture of glass. Sodium carbonate can also be used in soap preparation. Preparation of soaps. We have what we call additives that improve the quality of soap. One of them is sodium carbonate. Which one is the ideal site for the Solvay plant? The Solvay plant will need to be located near a river. Near a river. The reason why near a river is because large quantities of water is required for the cooling of the carbonator, because the reaction between ammonia and brine produces a lot of heat, so cooling is always required at that particular stage. That is that. Then we also have two other processes which are not very complicated. We have the manufacture of hydrochloric acid, then we have the fractional distillation of air, and we have what you call the Frasch process. These ones comes like diagrams. The one for Frasch, we need 3 pipes. These 3 pipes, one of the pipes passes superheated water. This is water that has been heated under very high pressure to make it have a temperature of around 170. And the role of the superheated water is to melt the sulfur in the deposit. It takes advantage that sulfur has a melting point of around 113, and that is why it can be melted by that water. Then the next pipe is the one that passes hot compressed air, which is used to force the mixture of sulfur and water to the surface. And then the other pipe usually releases the sulfur and water mixture to the surface. It is simply a diagram which does not come with a flowchart. Then also the manufacture of hydrochloric acid, we need hydrogen and chlorine as the raw materials. They are reacted to produce hydrogen chloride. Then they are dissolved via the glass beads to give us hydrochloric acid. The next process that we move to is now the metal extraction processes. And we start with extraction of sodium metal. Sodium metal is very reactive, and it can only be extracted by electrolysis of its ore. The 2 chief ores from which sodium is extracted are rock salt and salt chirepita. Salt chirepita is sodium nitrate. Rock salt is sodium chloride. The 2 metals, but the main one is actually the rock salt. You can see on our flowchart on the screen, we have written here the ores from which the sodium is extracted. Rock salt, which is the main one, has a very high melting point. Therefore, what happens is that the sodium chloride is melted using electricity and then mixed with the calcium chloride, which we have just gotten from the Solvay. The reason for adding calcium chloride is to lower the melting point of the rock salt from 800 to 600. Then the mixture is fed to what we call the hood, the down cell. The down cell, which is lined with iron wall filled with fire bricks. Then inside the cell, there are electrodes. The central electrode is made from graphite and acts as the anode. Then on the sides, we have iron, which is used as the cathode. Remember, iron is not used as the anode because chlorine produced at the anode may react with iron to form iron 3 chloride. Now, the mixture is normally introduced through a hole, which is placed on top. When it is inside there, the sodium chloride is decomposed by electricity. Because it's a binary salt, it decomposes to produce sodium and chlorine. The sodium ions will get attracted towards the cathode, where they gain electrons or they are reduced to give us sodium metal. And the sodium metal will be written as liquid. Chlorine gas, chloride ions migrate to the anode, where they undergo oxidation to produce chlorine gas. And the chlorine escapes through a hood. To prevent the sodium and chlorine from recombining, we instill something called diaphragm, steel wire diaphragm, which is placed on either side. And the role is to prevent the two from recombining. What property of sodium makes it possible to be collected at the top of the furnace? Because one, it is less denser than the electrolyte. Therefore, it's tapped at the top and then it is stored. The iron wall is lined with bricks to maintain high temperature so that the electrolyte does not solidify. And that is basically how sodium metal is extracted. So there are only two equations for the reaction taking place. At the anode, there is oxidation. Then at the cathode, there is reduction. I'm getting chlorine and sodium. What are some of the effects of the down cell on the environment? One, the chlorine that is produced may cause bleaching if it leaks to the atmosphere. Sodium, when it also leaks, it may combine with rainwater to form sodium hydroxide, which can also have adverse effects on vegetation. What are some of the uses of sodium? Sodium metal can be used as a coolant in nuclear reactors when it's mixed with potassium. Sodium can also be used to manufacture sodium chloride. There are many other uses. How do you test for the presence of sodium ions? You use what you call the flame test. You take a platinum wire or a glass rod, you dip in a solution that's suspected to contain sodium, and then you burn it on an aluminous flame. It will burn with a yellow flame to confirm sodium. Or simply take a piece of sodium and ignite. It will produce a yellow flame. How is sodium stored in the laboratory? Sodium is stored under oil. The reason is because it readily tarnishes when exposed to air. So that's why it is stored under oil. And remember, sodium is a group 1 element that has a configuration of 281. Next is extraction of aluminium. We finish with the ones that are extracted by electrolysis. You can see on the screen a cell in which aluminium is extracted. It is called the Hall's cell. The other one for sodium is called the down cell. Which are the main ores from which aluminium is extracted? The first ore is called the bauxite, which is hydrated aluminium oxide. We also have mica. We also have corundum, which is simply aluminium oxide. But the chief ore from which aluminium is extracted normally is the bauxite, hydrated aluminium oxide. Now, the process of extraction of aluminium involves several steps. First, the ore is grounded. This is in order to increase the surface area. Then from there, the ore is heated in order to expel the water. Remember, this ore of aluminium contains some impurities which must be removed. One of the impurities present in the aluminium ore is called silica. Another ore is iron oxide. Therefore, the purification process of aluminium ore relies on amphoteric nature of aluminium oxide. And this is done by adding to the ore concentrated sodium hydroxide. When the sodium hydroxide is added and then the mixture is heated, what happens is aluminium, being amphoteric, dissolves in the sodium hydroxide. Silica, being acidic, dissolves in the sodium hydroxide. When aluminium oxide dissolves in sodium hydroxide, it forms sodium aluminate. When silica dissolves, it forms sodium silicate. Iron oxide does not dissolve in sodium hydroxide. Therefore, we do filtration. Upon filtration, silica, sodium silicate, and sodium aluminate goes in as a filtrate, and iron oxide as a residue, and it is skimmed off or removed. Then how do we separate sodium silicate, and aluminium silicate? We do a process called seeding. And in seeding process, we bubble CO2 gas through the mixture, where aluminium hydroxide is precipitated. Aluminium hydroxide is precipitated through the process of passing CO2 through the mixture. Then the aluminium hydroxide is filtered off and then heated. Upon heating, it decomposes to give us now pure aluminium oxide. So we have now done what we call impurity removal. Then the aluminium oxide is then fed into the hull cell, which again, as you can see on this diagram, has what we call the graphite anodes in the middle and the cathodes on the sides. If you recall also for sodium, the anodes were in the middle, the cathodes on the sides. Then electricity is passed through. Upon electrolysis, the aluminium oxide decomposes into aluminium ions and oxide ions. The aluminium ions migrate to the cathode, where they undergo reduction to give you liquid aluminium. And the liquid aluminium is tapped off at the bottom because it is denser than the electrolyte. Then oxide ions migrate to the anode up there, where they undergo oxidation to give us oxygen gas. The oxygen gas, because of the high temperatures in the cell, occasionally may react with graphite. Remember, graphite is carbon. And during the reaction, CO2 is produced. And that calls for constant replacement of the anode because it gets wasted. So we must continuously replace the anodes. And the aluminium is now tapped off at the bottom and can be stored. What are some of the uses of aluminium? Aluminium can be used to make alloys. One of the alloys of aluminium is called duralumin, that is commonly used to make aeroplane parts. Why duralumin is used to make parts of the aeroplane is because it is lighter and it is also strong and also is resistant to corrosion. Aluminium can also be used to make aluminium foil. Aluminium can also be used to make electrical cables. And aluminium can also be used to make sulfurics. Please note that aluminium readily combines with oxygen in the atmosphere to form aluminium oxide. And remember, aluminium oxide is amphoteric. That explains why it's not advisable to wash aluminium sulfurics using wood ash, because wood ash is alkaline, and the sulfurics are made from aluminium, which readily combines with oxygen in the air to form a protective layer of aluminium oxide. Therefore, corrosion may arise. So that is how aluminium is extracted. The test for aluminium may not be very direct, but we may use precipitation methods to confirm the presence of aluminium in something. For example, when you add sodium hydroxide, formation of a white precipitate soluble in excess may confirm aluminium, zinc, and lead. Addition of ammonium hydroxide you may produce a white precipitate insoluble in excess to conform aluminium and lead. Then I can add a carbonate. If there is be no precipitation, then we can rule out that it's aluminium, because aluminium carbonate does not really exist. If it does, then it is readily hydrolyzed. So in our next lesson, we are going to continue and look at the other metals and any other industrial process that we had discussed previously. Thank you.
Cut.